Hold your hand up in front of you. The iron in the blood inside it, the calcium in the bones, the oxygen you're breathing, the carbon in every cell. Here's a fact that sounds like poetry but is cold. Literal physics. Almost none of it was made on Earth. It was forged inside stars that exploded before the sun was born. Every atom heavier than the simplest few was cooked in the heart of a dying star, blasted across the galaxy, and eventually gathered into the cloud that became our sun, our world, and you. You are, quite literally, made of star stuff. This is the story of how we figured that out, and how the stars built us. To feel why it's astonishing, we have to go back to the very beginning, to the recipe the universe started with. About 1308 billion years ago, in its first few minutes, the hot young cosmos ran a brief, furious round of nuclear cooking. And it made almost nothing. Out of that primordial fire came hydrogen, the simplest atom, a single proton, and helium, and a whisper of lithium. That's essentially it. Roughly 3/4 hydrogen, 1/4 helium by mass. A universe of the two lightest elements and almost nothing else. Why did it stop there? Because the cooking was over in about 15 minutes. The universe expanded and cooled too fast, and because nature hides a trap right above helium. There's no stable atom with 5 particles in its nucleus, and none with 8. The assembly line jams almost immediately. So the Big Bang left a universe that was pure fuel, and almost no substance. No carbon for chemistry. No oxygen for water. No iron, no calcium, no gold. None of the ingredients of planets or people. If the story ended there, the cosmos would be a cold fog of hydrogen forever. And yet, look at your own hand again. Look at the world. Carbon, oxygen, nitrogen, iron, calcium, phosphorus. The periodic table is real. You're built from a rich pharmacy of elements the Big Bang never made. So the obvious, enormous question is, where did the rest of it come from? For most of human history, we couldn't even ask this question, because we had no idea what stars were made of, or that they were made of anything at all. They were lights, fixed, eternal, untouchable. The idea that a star could be a factory, cooking the atoms of your body, would have sounded like madness. The answer would take a century to assemble, and it runs through some of the most remarkable people in science. A young woman told her greatest discovery was surely wrong, a contrarian genius who bet the existence of a nuclear energy level on the fact that we exist, and a husband and wife team who wrote the recipe book of the elements. Their combined insight is one of the most beautiful in all of science, that the atoms in your body have a history older than the Earth, a biography written in the lives and deaths of stars. To read it, we start with a deceptively simple question. They had to answer first. What is a star actually made of? You can't fly to one. You can't scoop up a sample. A star is a ball of fire trillions of kilometers away. For centuries, that made its composition seem permanently unknowable. One philosopher even used the stars as his example of something humans could never possibly know. He was spectacularly wrong, because the light itself carries the answer. When you pass starlight through a prism, it spreads into a rainbow. And crossing that rainbow are thin dark lines, like a barcode, at very precise colors. Each element, hydrogen, sodium, iron, absorbs its own exact set of colors, leaving its own unique barcode of dark lines. Read the barcode in a star's light, and you can tell, from across the galaxy, exactly which elements are burning inside it. Starlight is a message, and spectroscopy is how we learn to read it. By the early 1900s, astronomers were busily reading these stellar barcodes, and they made a natural assumption. The stars, they figured, were probably made of much the same stuff as the Earth. Rock and metal, iron and silicon, just extremely hot. It seemed reasonable. It was completely wrong, and the person who proved it wrong was a 25-year-old graduate student whose result was so shocking that she was pressured to disown it in her own thesis. Her name was Cecilia Payne. In 1925 at Harvard, she did something no one had quite done. She combined the new physics of how atoms absorb light with careful readings of hundreds of stellar spectra. She worked out not just which elements were in the stars, but how much of each. And her answer was staggering. The stars were not made of Earth stuff at all. They were overwhelmingly, almost entirely, the two lightest elements, hydrogen and helium. A star is essentially a giant ball of hydrogen. The sun is a hydrogen bomb that forgot to finish exploding. This was heresy. The senior astronomer reviewing her work, Henry Norris Russell, told her the result was clearly impossible and pressured her to write in her own thesis that it was probably spurious. So she did. She hedged. And then, a few years later, other measurements proved her exactly right. She had been correct all along. One astronomer later called it the most brilliant PhD thesis ever written in astronomy. Cecilia Payne had discovered what the stars are made of. And in doing so, she set up the real mystery, because if stars are just hydrogen and helium, then they are made of the same near-nothing the Big Bang left behind. So now, the puzzle sharpens. The universe is hydrogen and helium. The stars are hydrogen and helium. Everybody is made of the two lightest elements. So where, physically, in what furnace, did the carbon and oxygen and iron in your body actually get built? The first half of the answer is what makes a star shine in the first place. Deep in a star's core, gravity crushes hydrogen to unimaginable pressure and heat, millions of degrees. And under that crushing, hydrogen nuclei are forced to slam together and stick. Fusion. 4 hydrogen nuclei, through a chain of steps, fuse into one nucleus of helium. And here's the trick that lights the universe. The helium weighs a tiny bit less than the 4 hydrogens that made it. That missing scrap of mass is converted into energy. Einstein's E equals mc squared, and that is the sunlight on your face. This is the engine of every star. The sun does it about 600 million tons a second, and has for over 4 billion years. It's why stars last so long, and why they pour out light and warmth. Fusion turns hydrogen into helium and releases the energy that makes a star a star. But notice the problem. Fusing hydrogen makes helium, the second lightest element. It doesn't make carbon, it doesn't make oxygen or iron. The sun's main engine, running for its entire life, produces exactly one new element, and it's still one of the two. The Big Bang already made. So ordinary starlight by itself gets us nowhere new. To build a periodic table, a star has to get past helium. It has to fuse helium itself into something heavier, and that turns out to be shockingly hard. Because of that trap, the universe hit in its first minutes. Remember, there's no stable nucleus with 5 particles and none with 8. So the obvious routes are blocked. Add a proton to helium, 5 particles, and it falls apart instantly. Fuse 2 heliums together, 8 particles, beryllium-8. And it survives for less than a billionth of a second before it splits back apart. This is the carbon bottleneck, and it is not a small technicality. It is the reason the universe could have stayed hydrogen and helium forever. To make carbon, the backbone of all life, you'd need 3 helium nuclei to combine. But the middle step, beryllium-8, vanishes almost the instant it forms. How do you build on a foundation that disintegrates before you can add the next brick? For a while, this looked like it might be fatal to the whole idea. Some physicists suspected the heavier elements were made in the Big Bang after all, but the numbers never worked. The bottleneck killed that too. The elements had to come from stars, but the path from helium to carbon seemed physically impossible. The person who cracked it was a brilliant, stubborn, endlessly provocative English astrophysicist named Fred Hoyle, a man so contrarian he spent his life fighting the Big Bang theory itself. In fact, he coined the very name Big Bang on BBC Radio in 1949 as a vivid phrase for an idea he didn't even believe in. Hoyle was convinced the elements were forged in stars, and he refused to accept that the carbon bottleneck made it impossible. Carbon exists, he reasoned. We're standing on it. We're made of it. So nature must have a way through, and it was his job to find the loophole. And he found one of the strangest, boldest predictions in the history of physics. Hoyle realized that 3 helium nuclei could fuse into carbon, but only if carbon-12 had a very specific, previously unknown property. A special resonance, an excited energy level, sitting at just the right energy to catch the reaction as it happens. Think of it like pushing a child on a swing. Push at just the right rhythm, the resonant frequency, and tiny pushes build into a huge arc. Hoyle argued that carbon-12 must have an energy level tuned to exactly the right rhythm of 3 colliding heliums, or the reaction would be far too slow to make the carbon we see. Here's what made it audacious. No one had ever seen this energy level. Nuclear physicists had no reason to think it existed. Hoyle predicted its energy, around 7.65 million electron volts above carbon's ground state, purely from the argument that without it, stars couldn't make carbon, and therefore we couldn't be here to wonder about it. It's worth being honest about the history. Hoyle's original reasoning leaned on the observed abundance of carbon in the cosmos, not explicitly on the existence of life. That famous "because we exist" framing came later. But either way, the logic was breathtaking. He was using the very existence of the carbon around us to predict a hidden feature of the atomic nucleus. So Hoyle did something that theorists almost never do. In 1953, he walked into an experimental nuclear physics lab, the Kellogg Radiation Laboratory at Caltech, and essentially demanded that they go looking for his predicted energy level. The physicists were skeptical. The lab's director, William Fowler, later admitted he thought Hoyle's idea was far-fetched. But they ran the experiment. A team led by Ward Whaling bombarded a target and looked, precisely, at the energy Hoyle had named. And there it was. An excited state of carbon-12 sitting at 7.65 million electron volts, almost exactly where Hoyle said it had to be, the Hoyle state. Predicted from the existence of carbon, then found in the lab. Let that land. A man looked at the carbon in the world, reasoned that a specific, invisible property of the atomic nucleus must exist for that carbon to be possible, and the experiment agreed. It's one of the only times in science that we've successfully predicted a detail of nuclear physics from the simple fact that we're here to notice it. And here's why that resonance matters so much. It's finely tuned. If the Hoyle state sat even a little higher or lower in energy, the triple helium reaction would be far less efficient, and the universe would contain almost no carbon. No carbon means no organic chemistry, no DNA, no cells, no you. With the Hoyle state, though, the door swings open. Deep in the core of an aging star, a red giant, its center heated to 100 million degrees, helium nuclei slam together fast enough that the fleeting beryllium-8 in that vanishing instant catches a third helium at just the resonant energy. And carbon is born. 3 heliums become 1 carbon, 12. This is the single most important reaction for our kind of life. The carbon in your body, in every protein, every strand of DNA, every breath of you, was assembled 3 helium nuclei at a time. In the hearts of red giant stars, through a resonance a stubborn astrophysicist predicted before anyone had seen it. And once a star can make carbon, the floodgates open. Carbon can catch another helium to become oxygen. Oxygen can catch another to become neon. Suddenly, the star isn't stuck at helium anymore. It has a ladder, and it can start climbing the periodic table, building heavier and heavier elements. But there's a catch, and it's a beautiful fundamental one that decides the fate of every massive star and the origin of the iron in your blood. To understand it, we need to look at the one graph that governs the whole game, how tightly bound each nucleus is. Every nucleus has a binding energy. How much energy holds its protons and neutrons together per particle? The higher that number, the more stable, the more tightly bound, the more content the nucleus is. And when you plot it for every element, you get one of the most important curves in all of science. Here it is. Binding energy per particle, from the lightest elements on the left to the heaviest on the right. It rises steeply, hydrogen, helium, carbon, oxygen, climbing as nuclei get more tightly bound. It reaches a peak. And then, slowly, it falls again toward the heavy elements like uranium. And that peak, the most tightly bound, most stable, lowest energy place a nucleus can be, sits right around iron. Iron 56. Everything in the nuclear world wants to roll downhill toward iron. Light elements release energy by fusing up the slope toward it. Heavy elements release energy by splitting down toward it. Iron is the bottom of the valley. A quick honest footnote for the sharp-eyed, the single most tightly bound nucleus is actually nickel-62 by a hair, but iron 56 is the practical winner. It's the lowest mass, most stable endpoint that stellar furnaces actually pile up. For our story, everything rolls downhill toward iron is exactly right. This single curve explains why the periodic table looks the way it does, why the sun shines, why nuclear bombs work, and, most importantly for us, it explains the life and violent death of a massive star. Because a big star, fusing its way up that curve, is on a countdown to catastrophe. A star much heavier than the sun burns hot and furious. It fuses hydrogen to helium, then helium to carbon, then carbon to neon, neon to oxygen, oxygen to silicon, each stage hotter, faster, more desperate than the last, each one climbing further up the binding energy curve toward iron. And the star ends up layered like an onion. Hydrogen burning in the outer shell, helium below it. Then carbon, neon, oxygen, silicon, each heavier element in its own layer, fusing closer to the searing core. A whole periodic table being assembled in concentric shells. Each shell dumps its ash, the heavier element it makes, into the layer below, and the core grows heavier and hotter. Silicon burning, the final stage, forges the iron. And it happens fast. A big star can fuse hydrogen for millions of years, but its silicon burning, making that final iron core, can last as little as a single day. And then the fire stops, because the core is now iron, and iron sits at the very bottom of the binding energy valley. Fusing iron into anything heavier doesn't release energy, it costs energy. The star's furnace, for the first time in its life, has nothing left to burn. The one thing holding it up, the outward push of fusion, switches off. For a few billion years, that star has been a war between two forces, gravity pulling in, fusion pushing out, perfectly balanced. Now, in the space of less than a second, fusion loses. There is nothing to resist gravity. And a stellar core larger than our sun collapses, falling inward at nearly a quarter of the speed of light. This is iron core collapse. And what happens in the next few seconds is the most violent event in the modern universe, and probably the reason you have gold on your finger and iron in your blood. The collapsing iron core falls until it can fall no further, until its center is crushed to the density of an atomic nucleus, a ball heavier than the sun squeezed into the size of a city. And then it does something spectacular. It slams to a stop and rebounds, sending a titanic shockwave blasting back out through the falling star. The star tears itself apart. In an instant, it flares brighter than an entire galaxy of hundreds of billions of stars, a supernova. For a few weeks, a single dying star can outshine everything else in its galaxy combined. It is a death, but it is also a birth. Because the explosion does two priceless things. First, it takes every element the star spent its life building, the carbon, oxygen, neon, silicon, iron, all of it, and blasts it out into space, scattering the star's ashes across light years. And second, in the unimaginable heat and neutron flood of those few seconds, it forges brand new elements the star could never make in ordinary fusion. The heavy ones, beyond iron, that cost energy to build. For a violent instant, the universe pays that energy price, and elements far up the periodic table come into being. Here's how. Beyond iron, fusion is a losing game. So nature uses a different trick, neutron capture. Free neutrons, with no electric charge, can slip into a nucleus without being repelled. Pile enough of them on, let some convert to protons, and you climb past iron, building copper, silver, tin, all the way up to gold, lead, and uranium. Some of this happens slowly, over thousands of years, inside aging stars. The S process, which builds many of the medium-heavy elements gently. But the heaviest, and the fastest, the R process, needs a neutron flood so intense it only happens in the most extreme events the cosmos offers. For decades, we thought supernovae alone made these heaviest elements. Then, in 2017, we caught the universe doing it another way, and it was one of the most spectacular confirmations in the history of astronomy. Two neutron stars, the ultra-dense corpses left behind by earlier supernovae, each as soon as mass in a city-sized ball, spiraled together and collided 130 million light-years away. Gravitational wave detectors felt the crash, and telescopes, swinging to look, watched the kilonova, an explosion whose fading light carried the unmistakable signature of freshly forged heavy elements. That single collision is estimated to have forged several Earth masses of gold and platinum, flung out into space. So the gold in a wedding ring is almost certainly not from any ordinary star. It was made in the collision of two dead stars, or in the throat of a supernova, some of the rarest, most violent chemistry in existence. Step back and look at the whole cosmic assembly line. Different elements come from different places, a genuine division of cosmic labor written across billions of years. The hydrogen in the water in your body, made in the Big Bang, 13.8 billion years ago. The carbon and nitrogen cooked in the gentle deaths of medium stars. The oxygen in every breath, and the calcium in your bones, forged in massive stars and their supernovae. The iron in your blood, supernova iron. The trace of gold or iodine in you, from neutron-star collisions. Your body is not from one place. It's a cosmic anthology, a collection of atoms with wildly different origin stories, gathered from the Big Bang, from quiet stellar deaths, from titanic explosions, and from the collisions of stellar corpses, then stirred together into a single living person. And we didn't just guess this, we've watched it happen. In 1987, a star exploded in a nearby galaxy, supernova 1987A, close enough to study in exquisite detail, and its light gave us direct, real-time proof that a supernova forges new elements. Here's the elegant part. The explosion made a large batch of radioactive nickel, which decays into cobalt, which decays into stable iron, on a precise known clock. And the supernova's glow faded at exactly the rate of that cobalt decay. We could literally watch freshly minted iron being born from the ashes by the fingerprint of its radioactive decay. That's the whole thesis, confirmed in the sky in our lifetimes. Stars build the elements, and when they die, they scatter them. Every supernova enriches the gas of the galaxy with a fresh dose of the periodic table. And that enriched gas is the raw material for the next generation of stars, planets, and people. Which is exactly how we got here. About 4.6 billion years ago, a cloud of gas, already seasoned with the ashes of countless dead stars, collapsed to form our sun. The leftover debris, rich in carbon and oxygen and iron and gold, clumped into the planets, including this one, including everything on it. So the atoms in your hand really are older than the Earth. The carbon was made in a red giant that died before the sun existed. The iron came from a supernova. Those atoms drifted through space, joined our cloud, became the Earth, became the through chain, became you. You are the universe's way of assembling its own leftovers into something that can look up and understand where it came from. This grand recipe, which stars make which elements, and how, wasn't worked out in a single flash. It was assembled over decades, and its masterpiece is a single legendary scientific paper published in 1957. Everyone in the field just calls it by four initials, B²FH. The letters are the authors, two Burbages, Fowler, and Hoyle. Margaret Burbage, a formidable observational astronomer who fought sexism her whole career, at times barred from telescopes reserved for men, and her husband Geoffrey, William Fowler, the nuclear physicist, and Fred Hoyle of the carbon prediction. Their paper laid out, reaction by reaction, how stars build nearly the entire periodic table, the whole story we've just told, in rigorous detail. It's one of the foundational documents of modern astrophysics, the recipe book for the elements of the cosmos and of you. There's a bittersweet coda. In 1983, the Nobel Prize in Physics honored this work, awarded in part to William Fowler for the nuclear reactions that form the elements. But Fred Hoyle, the man who predicted the Hoyle state, who insisted the elements were forged in stars when others doubted it, was left out. Many believe Hoyle's habit of publicly attacking mainstream ideas, including his lifelong war against the Big Bang he'd named, cost him the prize. It remains one of the most debated snubs in Nobel history. But the carbon in every living thing on Earth is a quieter, more permanent monument than any metal. So the recipe is complete, from the Big Bang's thin gruel of hydrogen to the full rich pantry of the periodic table, built-in stars, scattered by their deaths and gathered into worlds. Which brings us back, finally, to you, and to just how much of you is, literally, stardust. Let's make it concrete. If you could weigh out every element in your body, here is roughly what you'd find. About 65% oxygen, 18% carbon, 10% hydrogen, 3% nitrogen, then calcium, phosphorus, and a sprinkle of everything else. Potassium, sulfur, iron, zinc, a whisper of gold. Now color those elements by origin. The hydrogen, about a tenth of your mass, is primordial, straight from the Big Bang. But everything else, the oxygen, the carbon, the nitrogen, the calcium, the iron, every bit of it was forged inside stars. By mass, roughly 90% of your body was cooked in stellar furnaces. You are, overwhelmingly, star stuff. And here's a lovely twist that depends on how you count. By mass, you're about 90% stellar. But by the number of atoms, it flips. Because hydrogen atoms are so light, there are so many of them that they're actually about 60% of all the atoms in you. So most of your weight is stardust, but most of your individual atoms are ancient Big Bang hydrogen. Think about that glass of water. Every hydrogen atom in it, 2 in every molecule, has been around since the first few minutes of the universe, 13.8 billion years ago. That water is older than the stars. You drink the Big Bang every day. And the oxygen bonded to that hydrogen? Made in a massive star. So even a single molecule of water in your body is a collaboration across cosmic history, primordial hydrogen from the birth of the universe, joined to oxygen forged in a star that lived and died billions of years later. Your body is stitched together from different chapters of the cosmic story. We can even read this history in the sky and the overall recipe of the solar system, measure how much of each element exists around us, and plot it, and you get a curve that is itself the fingerprint of everything we've described. There's a steep cliff from hydrogen and helium, the leftover Big Bang fuel still by far the most abundant. A deep valley at lithium, beryllium, and boron, fragile elements stars tend to destroy rather than make. And then, rising out of the heavier elements, a distinct bump, the iron peak. The universe is unusually rich in iron, exactly because iron is where the nuclear road ends. Every feature of that curve is a story we've told. The hydrogen cliff is the Big Bang. The lithium valley is the fragile elements. The iron peak is the binding energy curve made visible in the actual stuff of the cosmos. The abundances of the elements are the ashes of stars, and the pattern is their signature. And there's a zigzag writing along it, a sawtooth where even-numbered elements are consistently more common than their odd-numbered neighbors. That's a fingerprint of nuclear structure itself, even numbers of protons packed together more stably. The cosmos literally prefers even elements, and it shows up in how much of each one exists. This is the quiet triumph of the whole idea. It doesn't just tell a nice story, it predicts in detail how much of each element the universe should contain, and the measurements match. The theory of how stars build elements is written, correctly, in the abundances all around us, and in the composition of our own bodies. So the next time someone says, we are made of star stuff, know that it isn't a metaphor, or a poem, or a vague spiritual feeling. It is precise, measured, testable physics. The calcium in your teeth was in the core of a star. The iron in your blood rode a supernova shockwave across the galaxy. That exact phrase, we are made of star stuff, was made famous by the astronomer Carl Sagan in his series Cosmos in 1980. He put it perfectly. The nitrogen in our DNA, the calcium in our teeth, the iron in our blood were made in the interiors of collapsing stars. We are a way for the cosmos to know itself. It took a century of brilliant, stubborn people to earn the right to say that sentence and mean it literally. Cecilia Payne, who discovered that stars are hydrogen and was told she was wrong. Fred Hoyle, who predicted an energy level from the existence of carbon. The Burbages and Fowler, who wrote the recipe book. Each added a chapter. And what they uncovered is, I think, one of the most genuinely astonishing facts a human being can hold in their mind. You are not separate from the universe. Looking out at it, you are made of it. You are assembled from the debris of dead stars, briefly organized into something that can wonder about the stars that made it. Your atoms have traveled unimaginable journeys to be you. Some rode a supernova blast wave across the galaxy. Some floated for billions of years in cold interstellar clouds. Some were forged in a red giant, or in the split-second collision of two dead stars. And now, for a little while, they're arranged into you. Reading these words, understanding their own history. And when you're gone, when everything is gone, those atoms won't be. They'll return to the galaxy to drift and gather again, and one day be part of a new star, a new world, maybe a new someone. You are a temporary, thinking arrangement of eternal stardust, borrowed from the cosmos and one day returned. There's something freeing in that, I think, and something humbling. The same physics that built the stars built you. The same iron that makes a supernova's core is the iron that lets your blood carry oxygen right now, in this moment, so you can be alive to hear this. We spent this whole episode chasing a single question. Where did the atoms in your body come from? And the answer turned out to be the grandest possible, from the beginning of the universe, and from the fiery lives and deaths of the stars. Not one place. Everywhere. Everyone. So look at your hand one more time. Really look. Every atom in it has a biography billions of years long, written in the cores of stars you'll never see, that died so that eventually there could be a you. That's not mysticism. That's the finding of a century of careful, curious science. We are the ash of stellar fire, and the leftover breath of the Big Bang, briefly gathered into someone who can look up and figure all of this out. If that doesn't fill you with a kind of awe, I'm honestly not sure what would. Stay curious about where things come from, because sometimes the answer to a simple question reaches all the way back to the beginning of everything, and all the way out to the edge of the sky. The iron in your blood remembers a star. Isn't that something worth knowing? If this story stuck with you, do two quick things. Hit subscribe. Neat Science brings another forgotten story back to life, and there's a whole playlist of them waiting for you right now. And tell me in the comments, which part of this surprised you the most? I read every single one. So keep exploring. Your next story is just one click away. I'll see you there.